Hi guys again. So, in case you don't know, this series is made of problems for the capacitor chapter for 12 LS. We're starting from the easiest official exam to the hardest one. So find the video that fits your level and start from there. Now I'm starting with the first session, LS 2021. Okay? Okay. Now in this exercise, we have two parts, charging and discharging as usual. Okay, now the aim of the exercise is to study the charging and discharging of a capacitor. For this purpose, we set up the circuit of document 3 that includes an ideal battery that has an electromotive force E, two resistors. Usually we have only one, now we have two, so we have to be careful about it. Charging the capacitor now. As you can obviously see the figure, before I continue, I have position zero in the middle. This is where the circuit is open, so there's no current flowing. If I put the switch on the left side, position one, I will remove or I will avoid the right side of the circuit, which is here. But if I put the switch on the right side at position two, then I will have to avoid the left side of the circuit, which is this part here. Okay, now let's see the first part. The first part we have with the phase of charging of the capacitor. The switch K is initially at point zero, at position zero, and the capacitor is uncharged, obviously, as always. It's turned to position one and the charging process of the capacitor starts. At an instant T, plate B of the capacitor carries a charge Q and the circuit carries a current I. An appropriate device allows us to display the voltage UAB equals UR1 across the resistor and the voltage UBD equals UC across the capacitor. So we're just defining things now and we're defining the poles. UAB is for the resistor and UBD is for the capacitor. And as we can see in the figure, in the graph, we have two curves. One of them should belong to the resistor and the other for the capacitor. Okay, now in 1.1, they're telling us that curve A represents the voltage of the resistor. Why is that? As simple as that, because we know in the phase of charge, the capacitor is progressively charging, so it's taking the voltage of the battery. When it's completely and fully charged, it will not keep anything to the resistor. So the resistor was initially at its best voltage and it's progressively decreasing because of the increase of the capacitor. Or we can say that in a simple way, even simpler than that, which is we know that UR using Ohm's law, it's equal to R times I. And we also simply know that I in general, it has a solution I 0 E minus T over tau, which clearly explains that the current is decreasing. And by the way, the current is always decreasing in the phase of charge and discharge, which make the resistor also decrease. Why? Because if I is decreasing and R is a constant, then simply the voltage of the resistance of the resistor should also decrease. Okay, so how do we answer that? I wrote the solution so I can prove to you what is the formula that states that the current decrease. But what we have to write is I decreases over time. This is known in both cases, in the charge phase and the discharge phase. So UR also decreases. Now, the only thing that they can ask, doesn't R affect anything? No. And to prove that, we just have to write it so we can be sure that we're getting the full mark. Okay? And R is equal to a constant. We're not changing the resistance here. Okay? So since I decreases, UR also decreases. Since the capacitor, since the formula of the capacitor, the voltage of the capacitor by definition is CUC, since the charges are accumulated, are progressively accumulated on the plates, so U increases, because we know at the beginning the plates do not have anything, but after the current flows through, we will have some charges accumulated on the plate, which make us believe that Q is increasing over time, and since C is a constant, then of course UC is increasing with time. So curve A which is the one that is increasing, decreasing. So A is for UR and B is for UC. Now in 1.2, we have the time constant tau 1 equals R1C. Why is it tau 1 and R1? Why not simply R? Because in the circuit, as I said before, we have two resistors. And now we're working on the left side of the circuit, so we're simply just working on R1 right now. So we have to mention that. Okay, be careful. Now, using document 4, determine the value of tau 1. As I always say, tau 1 has three different ways to be calculated. Theoretical, using the formula just mentioned here, or graphical by finding where UC is on the graph at the 63% of its maximum value. Okay, so now tau 1, simply it can be R1 times C. Do we have that in the given? We don't have the capacitance, so we have to use the figure. Okay, now since the voltage of the capacitor is increasing, I have to find the 63% of the maximum value. And the maximum value, as I clearly can see here, the curve starts from 10, or it ends to having a horizontal asymptote at the end at E equals to 10. So this is E. Okay, so since I cannot use the theoretical formula, I have to use UC is equal to 63% of 10 volts when at T equals to tau, when the time is tau, not at any time. Okay, so UC is equal to 0.63 times 10, which is 6.3 volts. I go and I find where 6.3 is. It's approximately here. And I can see that the time at this point is 0.4 seconds. Okay, so using the graph, this is really important, by the way, how we can find tau. And some people ask, when can we use the tangent then? Don't use it unless they draw it for you. So tau is equal to 0.2 or 4, again 4. So 0.4 seconds. We calculated tau 1 specifically. Deduce the value in 1.2.2, reduce the value of C. Okay, so this is 0.1, now 1.2.2. Since we calculated tau 1, and now they want C, we know that tau 1 is equal to RC, R1C. Okay, since we know R1 and we know now tau 1, we can calculate simply C by saying that tau 1 is equal, C is equal to tau 1 over R. So C is equal to 0.4 over R1, which is in the given here, which is 4 kilo ohm. You have to be careful with the units too. Okay, so 4 kilo ohm, so it's 4 times 10 to the power 3. And as you can see, 4, we can remove them. We will get 10 to the power minus 4 farad. So as I always say again, the value of the capacitance should be small. Now 1.3, calculate the time T1 needed by the capacitor to practically become completely charged. We all know that when the capacitor is completely charged or discharged, we say that the time should be at least or greater than 5 tau. Okay, it's not 5 tau exactly, but we consider it approximately. So 5 tau, it's equal to 5 times tau, which is 0.4, approximately, which is 2 seconds. So we should have a time that is 2, at least 2 or more seconds, so we can say 100% that the capacitor is completely charged. Now here, we have the discharging phase. We put now K to position 2. Okay, so we're avoiding the left side of the circuit, but we have to be careful because we have 2 resistors now. Okay, so question 1, show using the law of addition of voltages. They don't have to say that. The differential equation for you, as I say, we write the addition of voltages first. So UC is equal to UR1 plus UR2. Okay, the capacitor is giving out to the resistors. Now the capacitor is simply, you see, I don't have to change it. Okay, now R1, UR1 is R1 times I using Ohm's law, and the same for the second one. But what do I know about I in the face of this charge? It's minus CdUc over dt. So I have to say UC equals R1, and instead of I have to put the new formula here, but I will put the minus just before, so I don't confuse between R1 and C. C duc over dt plus R2, and simply I have to replace I by its value, so I will put a minus before all of them, and C duc over dt. Let's take UC as a common factor, duc over dt as a common factor. What do I get? I will get duc over dt minus R1 minus R2 C. Okay, so I took C and duc over dt as a common factor. Now, what do I do with this negative sign here? I can simply throw it outside, and I will have plus here and here. And I can simply replace R1 and R2 by a capital R that relates both of them together since they are in series. Okay, so I will have UC equals minus C here. I rewrote it. Instead of R1 plus R2, I will say simply R duc over dt, and I can take this factor to the other side. So it's UC plus RC duc over dt equals to 0. And this is my differential equation. And by the way, in the phase of this charge, it's always equal to 0, not equal to E like the phase of charge. Okay, we're done with that. Now we have the solution. Find the time constant, as they always ask this question. We have to decompose that into few steps, and it's really easy to be solved. So don't panic, okay? The first thing we do, we write the solution. The second step we do, we find the derivative. Okay? So to find, I don't know what's wrong. So to find the derivative, I will rewrite everything, and I will just put in between the variable that it is next to the constant that is next to the time, which is minus and over tau 2. Why is it not working? Okay. Now we multiply them, we will get duc over dt. It's equal to minus E over tau 2, E minus T over tau 2. Now we will take the solution you see, and we will take the derivative, and we will put them instead of the differential equation. Okay, so what do we get? The differential equation is still clearly visible here. Okay, so we will have E minus T over tau 2. Alice, it's not working. Okay, plus RC, and instead of the derivative duc over dt, I will put the new expression, which is minus E over tau 2 E minus T over tau 2. The whole thing is equal to 0, and we take the exponential as a common factor. But in the phase of this charge, all of the terms have exponential. Okay, this is the best thing about it. So E minus E RC over tau 2. Why did I have this? Because the minus here, I will put it outside, and I will multiply all the physical quantities R, C, E, and tau 2 with each other. Okay, equals to 0. And we obviously know that the exponential can never be 0, so we will simply just put its factor equal to 0. So E minus E or C over tau 2 equals to 0, E equals E. RC over tau 2, we have E on both sides, we remove them. We will get 1 equals RC over tau 2. So tau 2, as we always know, it's RC. But what is the difference between R here and the R that we usually know? The R here, it's not simply R1 or R2, it's both of them together. Okay, we have to be careful about that. However, in the phase of charge, we only had resistor 1. So it's tau 1 equals R1C, not the general R. Okay, because the resistor 2 was in the right side of the circuit, which was not taken in the first question, in the first part. Okay, now we found the expression. 2.3, verify that the time needed, it's the same thing, same type of questions. How much time does the capacitor need to completely discharge? It's 5 tau. But 5 tau here, it's 5 RC, with R being R1 and R2 together. So we have to be careful here, okay? So it's 4 times 10 power 3, because it's 4 kilo ohm, each one of them, times C, which I just got in the first part. Here, I think, yes. Now you ask me, but this was calculated in the phase of charge. It's the same capacitance, because if we don't change the distance between the plates, or if we don't change the dimension of the plate C, it's the same no matter what phase we're in. Okay, so it's 10 to the power minus 4. Yes, 10 to the power minus 4. So what do we get at the end? 16 times 5. We will get 80, and 80, 10 to the power 2. So it's 8 times 10 to the power 3 seconds. Okay, that's it. So tau here changed because the resistance got higher. Okay, so it needs more time to discharge than charge. Now, the last part, duration of charging and discharge, show without calculation that T2 is greater than T1. Why did we take more time? I just said that. Why did we take more time in the phase of discharge? Why T2 is bigger than T1? T2 is bigger than T1 because simply tau is dependent on R and C. Okay, so in the phase of charge, tau 1 was R1C. However, in the phase of discharge, tau 2, it's not simply R1C, it's R1 and R2 together times C. Okay, and since R1 plus R2 is obviously greater than just R1 by itself, so obviously tau 2 will be greater than tau 1, which makes that the time needed to completely discharge, it makes it bigger than charge. Okay, as simple as that. If you like the video, subscribe, share, like, comment below if you have any questions. I can reply to the comments. Share your opinions so I can know which chapters to start with. And thank you for watching again.